Malcolm has been Professor of Coastal Engineering at the University of Rhode Island for around 40 years. And he runs Spaulding Environmental Associates. He also founded Applied Science Associates, ASA, in 1979, and that's been sold to RPS about 5-6 years ago. Malcolm, so the cluster I lead is based on renewable energy, and related to that, Malcolm has been lead senior advisor to the Ocean Special Area Management Plan, which assisted in setting the first, and it's currently the only offshore wind farm in the US, and that's sited in coastal waters of Rhode Island. Yeah, Malcolm specialises in modelling nearshore and coastal processes at estuarine, coastal and shelf scales, and he researches a range of topics through understanding hydrodynamics, waves, sediment transport, but he's probably particularly well known for his work in the transport fate and impact of oil spills in the ocean, in addition to search and rescue operations. But another of his research areas is flood risk, and that's the topic of his presentation this evening. So I shall hand over to Malcolm.
What I'm going to do is talk to you about some work that I've been doing for, it turns out, about the last 5 or 6 years. Talk to you about is coastal environmental risk and damage to infrastructure, and I'm going to be talking about infrastructure in its widest possible scope, all right? So the first thing was sort of if we head down this path, how do we make a system that would allow us to do this in any place at any time, any place around the world, for any kind of environment and climate. And that naturally leads you to some tool development that essentially is universally transferable and applicable. And so I came up with this idea for storm tools, and that's the underlying principle here. GIS-based for distribution. And I would tell you that if you want to bring someone to their knees, tell them about flooding in a given environment in terms of the numbers. And if you want to get their attention, show them a map of their house and how close the water is to their house. So under this initiative, we've been developing coastal inland flooding maps. And so these are quite common, but we've been adding sea level rise to them. And the reason is that all of our indications are that sea level rise will be important. And so for today, okay, we could design and build something, but if we're designing and building something for the future, we better well consider the effects of climate change. And the first order one would be sea level rise for coastal flooding. The next one is we've been working on is a coastal environmental risk index, and that's what I'm going to focus on. And the last one will be on design elevation maps, and that will become obvious as I go forward. So here's what the GIS interface of storm tools looks like. You can see the structure. It's organized under a special area management plan, which is a procedure we use in the US for coastal planning. So accessible to anybody, right now applicable to Rhode Island and being transferred to other locations. Here's an example of a map that we created for coastal area in Rhode Island. This thing is exposed to the open coastal ocean. It's a typical lagoon system, so inlet and then lagoon behind, and then development around. And you can also see evidence of turns out it's an old military facility, it's an airport. I would tell you that its use as the airport is stopped. It's the home of the jazz festival. Anyway, so you can get the picture here, and what happened is the underlying map here shows the impact of sea level rise, and it's got 1, 2, 3, 5 feet, right? So you can take a look at that and say, if sea level rise alone occurred, I am either at risk or I'm not. Here, and this is sort of what starts to make it a little unusual, is if we put the 100-year flooding on and sea level rise, that's what the area impacted is. And what you could see was 100-year flooding sort of takes care of a good majority of the flooding plain, and then additional sea level rise moves up the topography. And you can see that by the color coding, and the same cases as before. Okay, so the challenge that we had ourselves, or positioned ourselves, was municipal and state planning and management agencies need some way to take a look at an objective methodology to determine what what the risk is going to be and what the impacts are going to be, right? And ideally, you want to be able to have that index or tool be able to transfer knowledge about the problem to the community and the decision makers. And also, if you have some options about how it is you might want to respond. Okay, so one of the simple responses is, if a house is in harm's way, is to elevate it, or to protect it by some levee system, or neighborhood by that, or by diversion channels, or something similar. So if you have a tool that can allow you to do what the projections look like, you can get a tool that's useful for you to know what the implications of management decisions are. I would tell you that the guiding underlying principle here in terms of making decision making and permitting is what I call a risk-based permitting system. So in some permitting systems, one sets the standard and somebody else essentially has done the risk assessment, and the standard is set. We want to build there. Here's the standard. You build to the standard, right? So the problem now is that the conventional maps for flooding, as an example, where you would build to the standard, don't include sea level rise. So if you believe that sea level rise is going to happen, and there's pretty good evidence right now that we're seeing the beginning signature of it, and you're planning for the future, what you've got to do is you've got to essentially try to consider that. You might also want to consider the fact that the storminess might change and the storm impacts might change, but right now just consider sea level rise. Design life, right? So you set the design life. And then what happened is that sets the time in the future over which you want this thing to last. So a typical design life for a house might be 50 years. You have something that you're going to spend a lot more money on, going to be around a longer period of time, it might be 200 years. If you've got something you're really, really worried about, nuclear power plant as an example, you might think, well, I think I should do about a 5,000-year return period for the design of that. So the return periods that you decide on is based on the structure and its purpose that it serves. So you determine what the risks are of both winds and floods to that during that design period, and then what you do is you essentially go and do your design that way. State law doesn't allow the state to require people to do that. But what we did have done is we required them, when they apply for a permit, force them to go through the method that's here, force them to understand the risk that they face. They opt not to follow the guidance here. They can go back to the design standards in law, but what they have to do is the permit, where they've essentially assumed the risk, is registered on the property. So somebody else who goes and buys the property goes, wait a minute, you signed on for this risk. We can see the evidence of this already impacting the thing, and of course what will happen is that presses on the price. So it's not the ultimate long-term solution, but it's an important first step. So Coastal Environmental Risk Index, you can see its job. So the question is, if we, most indices have some number, 1 to 10, high, medium, and low. And the problem is that those risk numbers end up being pretty subjective, right? So what we've done is we have used damage that might be associated with an event to measure risk. So this house is 100% damage for this event, all right? Or this house is 75% damage. So the idea here is that we have a quantified number
that goes from 0 to 100, and we can have that per structure or over an area or over a region, and the differential between structures. So here's the underlying functional form of the index. So water levels and waves on the left, the structures and infrastructure in the center, wave and inundation damage curves, and recently we put on winds and wind damage curves. The output of that is the damage, either flood or wind, by individual structure. So this isn't this neighborhood or this structure type, it's that house, that hospital, that building. So that brings the focus home, right? It's not some generic thing that you go, oh no, it's not us. It's this is you, this is your house, this is your building. And the idea then is, of course, we can visualize it, which is what's shown in the lower left, or you can do the statistics, which is the probability distribution or the cumulative probability distribution or the like. So the underlying principle here follows the guidance that the federal government in the US uses, which is called FEMA, Flood Insurance Federal Emergency Management Agency. And their terminology and their methodology in terms of defining risk is shown in the little picture here. So the dotted red line this is the once in here flooding event. And what happened is, because the area got flooded, you get some waves. And what happened is the waves essentially increase the area or the potential height that it's impacted, and the waves decrease with distance towards the coast. And eventually what happened is, when at the very back where the 100-year flood transects with topography, the flood wave amplitude goes to 0. So the examples here show two houses, right? So here's two structures. This structure is really impacted. No matter how you do it, that's gone, right? His neighbor, although he's a little crazy, he's got his house a tad bit high, spoiled my view. Well, not really, actually, but okay. Spoiled the view of the people that are further up. What happened is that house has been elevated to avoid that risk. All right? And so that's one of the solutions that's used, particularly for essentially residences. The picture on the right essentially shows that in more graphic form. Okay. The flood insurance rate maps are the things that are used to set the building designs in the state. They're done for once in 100 year and once in 500 year. Buildings of house and residential structures are governed by once in 100 year. Other structures, as I said, if they're more important and more costly, longer design life. They use what's called the base flood elevation map. So base flood elevation is the picture that I just showed you previously, which is it's a combination of inundation and waves. So both of those things added together. And our local building codes, our state building code, the national building code, refers to these maps. So in the history, they keep updating the maps. You think they're perfectly fine, right? But when you do a design based on those maps, what you're doing is you're saying nothing changes fundamentally between now and whatever the life of the structure is. The return period analysis is the same. The kind of environmental conditions are the same. And that's not going to be the case. So maybe they're good for insurance, but they certainly are not good for designing buildings in the future in the coastal zone if climate change is important, which we think and suggest that it is. And I won't get into the problems, but the maps have really gross errors. I mean, they take your breath away. They're so bad. Somebody asked me, what was an example? And I said, well, we had two houses that were 100 feet apart, and the base flood elevation for the two houses was different by 500 feet, or by 5 feet in elevation. So this house over here had a 5 foot higher elevation for the base flood than this house. This person was really happy. This person was really unhappy. Neighbors talked to neighbors and said, how could that be? Well, I would ask you, if you are an engineer, how the water level could be 5 feet difference in 100 foot from a storm. And of course, it's not possible. Okay, so structure classification. The question is how to sort of group the structures. And this is essentially a method that the Army Corps of Engineers came up with. And so there's the categorization of the structure type. And I'm focusing on 4, 5, 6, and 7, which are the ones that are typically in the coastal area. So we typically don't have high-rise apartments close to the coast, or commercial buildings or residential or apartments, right? We do have a whole big group of single-family homes. And so 5A and 5B essentially are given here, which is no basement case, one single-story, multiple-story. So you can essentially take a look at that and say, oh, I can see how that works. And what I did was force the students to go out, and in a case where we applied this, I said, I want a picture from the study area you're working on of houses that meet this classification. All right, so you can see the startling one, of course, is if you look at 7, you can see that 7 is an elevated version, and of course 5 is just on grade or close to it. We essentially have damage curves then, which tell us, you tell me how high the inundation is, and I'll tell you the minimum damage, the most likely, and the maximum. And I will do that for both waves and inundation. So, and it'll determine which one gives the most damage. So I would tell you that if you have really large waves, it's not the inundation, but the wave that gives you the damage, and vice versa. So you go to the backside, the wave heights are really small. It's inundation that drives the damage. And the other one, so you have curves for both of those, and we also have content damage. So damage of things that are inside the structure. So you said, where in the world did you get these from? The Army Corps of Engineers, after Hurricane Sandy, which was the largest storm to impact the northeast coast of the U.S., went and did a detailed survey of all of the houses impacted in New York and New Jersey. And these data come from those experiments. This is one of my favorite ones. This is 3 houses. The one on the left is sort of a conventional house. We call it slab on grade. So no basement, 2 steps to get to the front door, 3 steps to get to the front door. Utilities are sitting over in a corner room somewhere outside the building. The second one is a house with a basement. All the utilities for the house, right? So the hot water tank and some sewage discharge lines and the washer and the dryer and all of that stuff is down there. And the last one is a structure that got elevated. The bottom axis is the distance from the first finished floor elevation of the structure, right? So if the structure is on the ground, the first finished floor elevation is here, and it's the difference between there and wherever the water is. Okay? Now, you take a look at 0. So the first one has no damage at 0, which you would guess is the case, right? So the water didn't get to the first finished floor, there's no basement, nothing to damage. The second one has a cellar. And look what happens to the damage. 10, 15, 20% already without the water getting to the height of the first finished floor. And the reason is impacted all of that stuff at the basement. And the last one, of course, is the elevated house. So, and in that case, the 0, of course, what we've done is we've changed the first finished floor elevation, right, relative to grade. And so what then happens is it's the height above that. But take a look at the difference in the slope of the damage line. What do you notice about the third one compared to the other 2? Much sharper, right? So elevating your house takes you out of harm's way, but if the water gets up there, then what happened is you have a really large load that is really above the ground. So picture pushing on the very top of these piles. All right, so that underlying principle is inherent in these maps. The wind stuff I won't talk about in detail, but the wind classification gets down to the sort of the shape of the roof, the nailing schedule, how the sheathing is done, whether you use 6 penny nails, 8 penny nails, and whether you use hurricane straps or no straps, but I won't do that. And this is wind damages, so I won't spend any time. So the question is, start off with sea level rise. Okay, if you're a climate denier, sea level rise is actually going down. We're not only having no sea level rise, the sea level is going down a little bit. If your tomorrow looks a lot like today but a small change, then you take the history, and history says you know, we've got a couple of inches here every 10 years, right? If you take a look at any of the climate simulations, depending on what you decide to do, you end up with a curve that shows some acceleration. And people who've done this say this is sort of baked in, so it's hard to get out of these. And what we're actually going to see is, depending on what it is we decide to do about low carbon future here, which curve we follow. For planning purposes, and to be conservative, the group that I've been working for as a state agency has adopted what's called the NOAA high curve. Right? So they're hedging their bets that says these guys could be wrong, and I'm not going to just sort of take a couple of feet over 2100. So from the time we started the project, when I began the project in 2017, once in the 2100 projection, which is the 100-year, we were dealing with 5 feet. And it turned out that they moved the number up to 7. And they just now moved it to 11. All right, so that's the planning horizon that the municipal organization is using for sea level rise, right? This, we wanted to sort of understand what it was that we had at risk of the state. This is a picture of the state of Rhode Island. We have the benefit of being the smallest state in the United States. So a small, if you slightly doze while you're traveling, or your text message runs a little long, you just ran out of the state. So you went from one state to the other. So the state's 40 miles wide and 60 miles high. So I'm not kidding, right? Anyway, the center core of the state is a bay with this thing wrapped around, and we are in an area where we have a lot of residential structures. So we essentially did sea level rise calculations, 100-year storm, and we took a look at the complete distribution of housing in that area and created this hotspot map. So the hotspot map simply says there's a lot of structures that are concentrated in these locations that are in harm's way, right? And you look at that and you say, okay, there are some key areas right here, and a combination of low-lying topography and really dense populations that are really in harm's way. And there's a bunch of others that are, the topographic relief is higher, or the distribution of the houses is greater, and so less impact. So this is a map we started with to decide which area we would work on. Okay. The other little interesting thing is, because of the shape of the bay, so relatively narrow, so 40 miles by 6 or 7, when the surge comes up, you get an amplification. So the amplification is from the mouth to the head of the bay about 35%. Could be as high as 60% and as low as 15. The tide is amplified by about 30%. So important implications in terms of surge, which is using the surge height from the gauge that's closest to the ocean, is really a bad idea by about 35%, right? And so those areas at the upper part of the bay, there's a lot of housing there. They are really in harm's way from a surge, but also because of the amplification. All right, so here's the method applied to a coastal community. This is called Charlestown, Rhode Island. And this is located, you can see Rhode Island, the boundaries of Rhode Island are given here. We chopped it off because we don't like our neighbors from Massachusetts so much, so we were unwilling to give them any picture of what went on. So we cross over Mount Hope Bay. Part of it's in Massachusetts, not us. Could have been in another country. We're just messing with them a little bit, but okay. And down here, the same thing. This is the foreigners from Connecticut. Anyway, we did our own analysis there. Anyway, the area here is completely exposed, right? So open ocean directly to the south. Hurricane Alley. So if we get hurricanes in the area, all come from this way, like this. So our worst hurricane did this, and one of our worst ones, and another one did this. So we end up at the end, if a storm is blowing up the east coast as a hurricane, tropical of origin, what happened is we typically get kissed by it if it lives long enough. And north, turns out, north of this is called Cape Cod. North of here, the storms are extratropical in origin. And so storms from the north, right, from the north and west dominate there. And for us, it's south and west. All right, so different dominance in terms of what's driving the events. So there's some little shots of some of the impacts from the two largest storms. 1938, which was about a 300-year storm based on current analysis for return period, and Carol, which was in 1954. The first one was Category 3, the second was Category 2. Both of them had transport from the west of the site, putting the state in what's called the right front quadrant of the storm. So surge or winds and the forward motion of the storm are additive in the right front quadrant, and they subtract left, right? So the worst place to be in a hurricane is right front coordinate, and the worst time to be there is really fast forward velocities. So it turned out that 38 hurricane passed over Rhode Island in less than an hour. So 60 miles an hour forward velocity for this storm. Okay. Anyway, you can see the area. This Charlestown is right here in the background. Here's the inlet to the pond. You can see these before. And this of course is remnants of prior events, right? Which is, these are called washover fans. So the sediment gets eroded from the shoreline. Part of it washes over into a fan that goes on the backside, and part of it gets taken away offshore, and part of it goes as longshore transport. This is a picture of the same area. This is that same barrier, and it's after the 54 hurricane. And you can see what happened here. These are called surge channels. So this is where the dune breaches and the water starts to connect. And once it opens up, right, even though there's only one inlet, suddenly you have multiple inlets. So the pond completely floods, and the protection that the dunes gave the area are gone, right? Okay, so here's the application. We start. If I said to you, I would like to know the location of every single house here. So I started with that. Okay, here's the location of every single house in this part of Rhode Island for this community. Okay, so students, there's a prize. You visit 100 houses, and you tell me what 100 are. And you go with your phone and take the GPS locations of them. I give you a gift, a party, right? Or I call the emergency number. You know that 911 number in the United States is for emergencies. So you have a problem, you're having an accident or something on the highway, or your home is on fire, you dial 911. In the 911, they maintain a database of all structures and infrastructure in the state. And so that database essentially has the location of all of the structures and by classification. So there are all of the structures that are located in our study area, by their classification, which is the type of home that it is. So they have single, multi, mobile, and then other, and then seasonal homes. Here is essentially the distribution of structures by the structure type. So this is essentially using the classification system that the Army Corps of Engineers has come up with. So we have them by classification. And what I would tell you is you can see these houses here are some kind of elevation, right? And the houses back here end up being 1 or 2 stories with or without a basement. All right? So, and you can see this relatively sharp, really sharp dividing line here. It turns out there's a small bridge located right there, and that bridge is the only access to this part. And here, what happened is this is mainly protected, so you don't have any development here because we kept it off. And you end up with, this would be a headland, so this is a barrier, erodible beach, and this is a headland here, and there's another headland over here. So you can see a lot of development on the headlands and on the backside of the coastal ponds. So this is what the flooding looks like. So this is once in 100-year flooding. And these numbers are base flood elevations, or this is the surge height, right, from a 100-year storm event. And it's NAVD 88, so it's not grade. People make the mistake of showing you grade information when they really meant it's the common reference. Turns out that common reference NAVD 88 for this location is within 9 centimeters of mean sea level. So this is like looking at a mean sea level, and what you're seeing is the elevation of the water relative to that, right? So not elevation local to grade, but elevation related to the benchmark. This is wave heights with the loss of the dunes. So what you can see, if you closely take a look at the wave height here, and then look at it here. So you can see the wave heights are really large, right? So what's happening is you get these really large offshore waves. What happened is they're breaking. And they're breaking right along the topography. And so some of the water gets over the barrier because it's inundated. And so you get waves on the back side. And then the waves dissipate because they continue to break. So this is the wave height, right? No dunes, so here's the total inundation with everything, right? This depth is the depth relative to grade, right? So inundation depth, so that means I'm on the ground, this is how much water is at my location, right? Versus I'm on the ground over there, the water level is different, all right? But you get the point. Closer to the water, you're in trouble, and as you go back, less. That's what happens if you have 2 feet of sea level rise. Seven feet. So none, 2, 7. Okay, so if you're planning 50 years, what we're recommending to people is they look at that map. A couple of feet of sea level rise clearly in 50 years, no matter sort of how you play this stuff out. Okay, so we go through now, and we essentially now have these estimates of the base flood elevation maps, and we have them as a function of sea level rise. And now what we do is we look at damages. So for every structure, that's a dot there, every one of them, we have damage estimates. And I think it wouldn't surprise you that those that are closest to the coast end up, right, having really large damages. even the ones on the back side of the pond have large damages. And the reason is it's a combination of the water level, but also we get wave generation in addition as the wind blows across the pond. So we get some regeneration. And then what happened is we get it on the margins here, right? Here we end up seeing sort of differences, you know, really closely spaced differences. And those turn out, and I'll show you that in a little second. So there's 2 feet of sea level rise. And there's 7. So we switched over the symbols here. We've added 2 new symbols. Below mean sea level means there's water in your front yard, right? So your house is no longer viable. And black means the area got eroded, right? So the projection for future erosion in the future says your property is gone. Okay, so if you're planning and you're thinking about buying a house or building a house, this might be useful information for you to look at. So here's a classic example. I said to the students, I said, can we sort of pull out a real example with houses that are side by side that have dramatically different damages, right? So the same water level, but different house structures about what the damage profiles look like. So there's an example. So this is not Photoshop. Those two buildings are side by side. The one guy on the left opted an elevated structure, and the guy on the right didn't. And this is without any sea level rise. All right, so even if you think no sea level rise is going to occur at all, the guy on the right's in trouble, right? I would tell you, if you're paying insurance on your house, flood insurance, and if the flood insurance is tied to your risk, the guy on the left's risk is really small, and the guy on the right's risk is really high. And what's happened is the flood insurance program in the United States has protected people from paying their fair market value for flood insurance. And that's why the guy on the right is allowed to keep his house. Because if it was damaged, they would currently repay, and right? And if he had to do it himself, he would not be there. He would have moved out a long time ago. All right, in presenting this stuff, we do more than a few presentations to municipal audiences, and there's a lot of people who go, if I could just go home soon, I'm thinking of that glass of wine and or sherry, and then I'm going to go to bed. And they want to catch their attention. They say, okay, so let's look at some visualizations, right? So this is a case of, this is the dune is intact. So we've assumed that the dune didn't fail, all right? Not the case, but that's what we assumed here. And that's the coastal inlet, which is a stabilized inlet to this small pond. And what happened is here you can see the area that's inundated, you can see the color. And the scale there at the lower right tells you the percent damage. Okay. That's what happened if the dune erodes. Right? So if the dune were protective, you would get that. And the dune is not protective, right? Some serious additional impact. So you can see all of the houses along immediately along the coast here, all of these houses essentially are gone with the exception of that one. So I'm betting that that house is elevated seriously, right? Anyway, this tool then allows you to sort of get at that level of detail. And that's with 2 feet of sea level rise and 7. So you will notice what we've done is, if it goes to 7, those structures that are below mean sea level and those structures that have been eroded away, we essentially have taken them out. So watch. Okay. So this is the base flood elevation map that we came up with. So the structure of this is, you can see you've got really high, and this is NAVD 88 reference, so this is this constant benchmark. You've got really high water levels, 20 feet along the coast, larger than 20, and then some places inside as much as 20, and then drops as you go further in. Here are the maps that FEMA uses for selling flood insurance. Now, just so that you can compare and contrast them, the color scale is exactly the same. So, what do you think? Have you heard of Irma and Harvey? They have the same issue with the flooding maps there. But that shows you what they actually look like, right? So those are back-to-back maps. One doing state-of-the-art tools and the other one doing FEMA, and there they are side by side. So my little case example that I introduced was right there. One guy is complaining bitterly about paying flood insurance, and his neighbor says, look, it's not a problem. I come over for a drink. My flood insurance has just gone down. My water level is lower than it was before. I'm happy. I'm wonderful. The other person said, geez, my flood insurance just went up. How could we be 100 feet apart? And you can see how that would play out administratively. In rolling out these maps, we went to the municipal government, which we had done them for, and they were having a heart attack over showing the individual damage to property. And they said, yeah, if we show those, it'll be terrible. I said, why? And they said, well, we don't want to do that. And I said, how about if we put together a thing called a risk map? And they said, okay. And what would the scale be? And I said, well, so low, medium, high, and extreme. I said, we like that. And it doesn't have any house, that house, right? So we put together this risk map for them, and so red is high, and of course, yellow is green or lower. So I just wanted to make sure that they felt good about this. And so we blew them up and said, so there you go. They said, oh, we like those, right? So this is 100-year, sea level rise, 0, dune eroded. So you can see, I tell you what we did is we pretended there was a house located at every location in the domain and calculated what the damage would be if a house was at every location, and then told them there were no houses at those locations. These were simply risk maps. So they got the contour maps, they get a chance to tell the story, but they don't have to point to individual X or individual Y, they point to a location. So I overlaid the actual results of the Siri calculation, and they're there, and you can see that the colors are exactly the same, right? And there it is with 7 feet. So 7 feet, and we've also used the color, right? So inundated by 2100, so you can see the change. And there they are side by side. All right, you've seen how this works. I'm going to go through one more community, as they say, really fast, because you've seen how it works. This community is up inside the bay, so it's given by the circle here, right? Okay. So, sea level rise maps. Can already begin to see the problem. It's got this thing, this sort of neck that sits there that divides this piece of land right to the mainland. Here's what it looks like with surge, 100 feet. You can see this thing separates, right? I would tell you that when the municipal planners first saw that, the emergency response vehicles for this area, to cover this area, are located on that location. And we suggested that in an emergency they might have Plan B, since access was not going to be provided. So there's all the structures. There is the structures by classification in the flood zone. So you can see nobody elevates, right? Because they think they're far up in the bay, so no problem. Don't have any wave environment. They forgot about the amplification, and so no pile-based structures. Surge maps, wave heights. Wave heights are really quite modest. The difference here, you see this thing here and this one here? It's wind exposure along the central axis of the bay that exposes those two locations in that pocket. And then of course, this is all protected because of the geometry. And this level of detail, this resolution is down to a meter. So it gives you, provides this really, really high resolution map of what's going on. So sea level rise, none, flooding. Here it is, base flood elevation, 0. Right? Here's total inundation, 2 feet of sea level rise, 7 feet of sea level rise. Here's the sea level impact, no sea level rise. Most places, no problem, right? 2 feet, 7 feet. So that tells you what structures are at risk. Here's a map from that point that was showing erosion looking back. This is called Warwick Neck for the obvious reason that as water level comes up, it's increasingly like a neck, right? With this head offshore and then the mainland behind it. 7 feet. Base flood elevation maps, just as I showed you before. FEMA maps. Look at them side by side. The ones on the left are our analysis, and the ones on the right are FEMA's analysis. So what's happened, of course, is their spatial resolution is, you can see, it's really sort of terrible. The spatial resolution is down to a meter. So you got all of this detail here and nothing there, right? Much higher here than there, and the reason is they don't have as big an amplification for the surge going up the bay, and they have lower wave heights. All right, here's the risk maps, side by side. All right, almost done. All right, so the question is, all right, we got this all operational, we've rolled this out. We've had 3 undergraduate classes working on senior design projects on applying this to different areas, adding wind. They're doing it to a case where there's a hurricane barrier protection. We've added wind analysis to include in this as well. And we're rolling this out, and this will be embedded in the permitting system for the state. And the question is, how is it that you connect with people to help inform them of their risk and help them to work with the municipality or their builder or whatever to enhance the coastal resilience? And the issue is communication and understanding of the risk. Well, I would tell you that if you tell the average citizen you have this really nice program that they can connect with, and it's at this website, they nod, and it doesn't happen. So we said, how is it that we could connect with these people, get them to understand the risk, and help them make decisions, and make it simple, make it so, and I thought, if you watch these kids go along, a kid never leaves his cell phone in his pocket for very long, normally stored in the back pocket when it comes home. Right? Yeah, there you go. Anyway, they're starting, I think these cell phones are given out at 4 years old, aren't they? No, just kidding. Anyway, so a lot of people end up using cell phones, and they're used to taking this initiative. And so what happened is we are developing a cell phone app that would allow you to walk over to this place and say, I'm here. That's this kind of structure. Goes to the database and finds out what the risk profile of the structure is, and you say, I want to know the damage. And you say, you know what, suppose I were to elevate the structure. So I had to change the elevation, right? What would that look like? And what would happen if I used design criteria set by the state versus the design criteria that include sea level rise effects? So the idea is that the cell phone would have all of those applications. So the design, life, type, and location of the structure here, the flood characterization here. So this is base flood elevation for different sea level rise scenarios, setback lines, free allowance space, freeboard requirements. What the wind environment is for design for that location. So these are wind speed contours. Here's the flood risk maps that I showed you, which is showed you for Charlestown and shows you rather than show you at a discrete location, it shows you in the neighborhood. I also would tell you that if you are worried about evacuation from your house, you can look at the risk map and say, got a 100-year storm, and I bought a house over here, I couldn't get out, right? And so this would tell you that. And then the final one would be essentially flood and wind damages, give you actual numbers. Okay, so here's the summary. Risk and damage method using state-of-the-art techniques and tools. This is sort of an integration of modeling and data and observations from, this is very recent events, right? So the damage functions are from Sandy, from New York and New Jersey. It's web accessible, so anybody can pick it up. What we do is we make it web accessible, we let the town go through and decide, then they can make it accessible, we can make it accessible at the university. We also make accessible the download for the layers. So if the municipality wants to use these in some of their own planning, they can do that. Essentially, design life permit-based. It's objective, an analysis, right? There's quantified, you quantify the uncertainty in it as well. That can give you an estimate of lower risk, the upper risk. You can essentially see what your risk tolerance is at sea level rise. The maps that I showed you have proven very effective at communicating this risk. There's an explicit consideration of sea level rise, and the one that you pick, you can pick the 100-year and 2 feet of sea level rise, which makes you think that you're going to do a 50-year kind of return period or 75 years. So it allows you to sort of explore what those options are. And then I would tell you that you can convert this to money. You could sit there with a builder and go, okay, here's what I'm thinking about. Can also, I would tell you, with an insurance agent, you could essentially say, here's what I'm thinking about at this location. What would you think that the flood insurance might be, premium for that? So the idea is, again, to provide that information. As I said, one of the most powerful aspects of the tool is we went through an exercise and said, what would happen if every time somebody rebuilt after a storm, they were forced, if they got flooded impact, they were forced to elevate their house? How would that change the profile for the town of how would it change the overall risk and reduce the risk for the town? And then it's consistent with the existing frameworks. So this is essentially an acknowledgement to the Storm Tools team. We've been working for, this is 4 years now into this. So we've had 7 projects so far, and the project on the cell phone app just got funded. So with that, I would also like to thank the folks here for inviting us over to give a talk and presentation. This is renewable energy, but in a different form, but at the core of the issues related to low carbon and a methodology that allows you to sort of really dig down on these issues. The things we have in progress are adding roadways, bridges, sewage treatment facilities, and hazardous waste facilities, both the storage and the berm, containment berms that are around them. And we have all of those that are currently in progress. So with that, I'll stop on time.